All right, so let's go ahead and get started on today's content. Again, not a surprise, we're continuing talking about even more limits. But the good news is that today should be our last one where we're introducing new rules for limits before next week we talk about finally the derivative, if I remember correctly. Let's see, did someone steal the pen for this classroom? That's going to be unfortunate, but I will make do. So today, let's go ahead and talk about limits at infinity. Infinity. So far, we've talked about what happens whenever we take the limit as x approaches a finite number. For example, we did the limit as x approaches 4, as x approaches 49, as x approaches -8, something like that. Now we're going to talk about what happens whenever x approaches infinity. First off, what do I mean exactly x approaching infinity? What does that exactly even mean for me? Any ideas? What does it mean for x to approach infinity? Because we know infinity is not really a number. So what does that even mean? Any ideas? Any positive number? It is going to be a little bit related something to that. We'll see in a moment. So if I'm talking about as x approaches infinity, this will mean that x continues to grow. It keeps on getting larger and larger and larger. So what does that mean for as x approaches negative infinity? Because we have positive infinity, we have negative infinity. If I say x approaches negative infinity, that means it becomes larger in the negative direction. So it goes from like negative 10,000, negative 100,000, negative 1 million, negative 1 trillion, so on and so on. In other words, as we approach infinity, we are just meaning it's going to grow in the positive or negative direction. So let's go ahead and look at this picture that I have here. And this is actually going to be our example one. I'm going to give you this graph. Let's see, given the graph of, let's say, the function f of x is equal to 1 over x plus 2, comma, find out what is the limit as x approaches infinity of my function. And I will give you a graph in just a moment, right now. Make sure I draw this correctly. All right. 2, 3, 4, 5, so on and so on. Where's my function? There we go. So if my graph looks roughly like this, let's talk about the limit of this function as x approaches infinity. So, as I said, x approaching infinity means that x is growing larger and larger. In other words, I'm looking for as x continues towards the right. Because then this is my x direction, left and right. Going off to infinity means I'm looking as it goes all the way to the right, endlessly. What does it look like? What's happening as I go further and further right? What do you think is happening with my y values on my height? It's getting closer and closer to a certain value. It's getting closer to a height or y value of 2. So you can see here, this is 1, 2. If I wanted to, I could draw an imaginary line here just for emphasis. I can see that this function appears to go further to the right, and it's going to get closer and closer to this dotted blue line, but it's never actually going to touch 2. However, even though it doesn't touch y is equal to 2, that's fine. We're talking about a limit. We want the number that it's approaching or getting closer to. In other words, I'm going to claim that this limit is going to be a positive 2. While we're at it, does anyone remember what is that name of that imaginary dotted line that I don't actually cross? Starts with an A. Asymptote. Specifically, it's the horizontal asymptote. So the limit as x goes off to infinity, that is, as x continues to grow larger and larger, my graph slowly but surely gets closer to 2. Would there be any difference in this particular problem if I wanted the limit as x approached negative infinity? What would be my limit? Would it still be 2 or would it be something different? Okay, so the limit as x approaches negative infinity. So first off, as x approaches negative infinity, am I looking to the far left or the far right of my graph? Far left, because x approaching negative infinity means I'm getting larger and larger in the negative direction. So I see I'm just following the graph to the left, and I see where is my graph approaching height-wise. So yeah, it's approaching also a height of 2. So in this case, my limit as x approaches positive infinity and the limit as x approaches negative infinity of my function, they're both positive 2. And as you can probably guess, this is going to be closely related to how we're going to view horizontal asymptotes. Any questions about how I got positive 2 as my answer here? We are technically talking about the same concept, but then the key difference is that I'm not drawing this vertical dotted line because, again, infinity is not really a number. I can't draw an imaginary dotted line at infinity or negative infinity. All right, so what if I had something like this? You don't have to draw this next one. This is a very quick problem. So what if I had a function that did this? There we go. What would be the limit of this function as x approaches positive infinity? What do you think that would be? Infinity. So why can we say that the limit, in this case as x approaches infinity, let's call this h of x, for example, is equal to infinity? Why is that the case? Yeah. So if we use that same logic as before, x approaching infinity, I'm looking what happens if I keep on going right. I look at this and I say, well, it doesn't look like it's approaching any single value. It's going to keep on just going up, higher and higher. In other words, we've seen it whenever I say x is getting larger and larger in the positive direction. This is me saying that my function is my limit, is going off to infinity. What about if I take the limit as x goes to negative infinity? What do you think my solution may be? This one's going off to negative infinity. Why exactly? Pretty much, yeah, pretty much the exact same thing. If I look on the left, is my graph going downwards or upwards or stopping at some point? It's going down towards negative infinity. There's one thing I want y'all to be careful about here. Just because my limit was as x goes to negative infinity, that doesn't mean my limit is negative infinity. In other words, it was just this example where I said this is negative infinity, and then this one also happens to be negative infinity. I could have easily flipped this entire picture and had the sign flip as well. So what we just introduced was what we're calling limits at infinity. This is different from the ones we did before where we had infinite limits. So infinite limits is whenever we have a limit, it's equal to infinity or negative infinity. Limits at infinity is whenever I have this expression at the bottom. And as you can probably tell, there is a little bit of overlap. All right, so any questions about this quick example or example one? All right, so let's see how does this relate to what we did with a horizontal asymptote. I'm going to quickly look back at this. My limit as x approached infinity was 2. Where was my horizontal asymptote? 2. I'm going to go ahead and make a statement here. Do I want to call this a definition or a proposition? We'll call it a definition. So our first definition for today. So we say the line y is equal to L is a horizontal asymptote. Let's see if I can fit horizontal in here. Oh, I'm not going to try that. Horizontal asymptote. Asymptote of the curve y is equal to f of x if we have that the limit as x approaches infinity of my function is equal to L. In other words, if I take a function, I take the limit at infinity, and it's a number, just like how before we took the limit and we got 2, this tells me what is my horizontal asymptote. So before, in example 1, my horizontal asymptote was y is equal to 2. So this is how we're defining a horizontal asymptote. And again, depending on what math class you might have taken before, you might have done some work in algebra where it was like, find me the horizontal asymptotes, and then you had all these rules going through all of them. And actually, if we were to really dig into it, it was actually introducing a limit in a sense without actually calling it a limit. So in this section, we're going to talk about how do I evaluate the limits at infinity if I have some rational expressions in particular, and how do I find the horizontal asymptote. Because if you can evaluate the limit at infinity, you automatically have the horizontal asymptote. It's y is equal to whatever number you get. So to get some practice, let's go ahead and do our second example. Example 2. Same instructions as per usual, evaluate. Part A. Well, let's start off with the limit as x approaches infinity. Let's do negative infinity while we're at it, actually. 4x to the 16th power. I'll write b while I'm here. For b, what if I do the limit as x approaches as x approaches infinity of 1 over x. And I'll do a part C in a moment. But I'll let y'all write this before I go any further. So without even thinking about the graph, I should be able to evaluate these. Let's start with part A. The limit as x approaches negative infinity of 4x to the 16th power. Do we have any guesses about what can I even do here, or what my answer might be? Positive infinity. Let me write that first. Where are you getting positive infinity from? Yeah, if we look at this, the first thing is I know that this should be a positive value overall, right? Because if I plug in any negative value and take it to the 16th power, it's positive. A positive number times 4, that's still positive. But how did I know exactly that it was infinity? I agree, positive. How did I know that it's going to be infinity, though? Or give me some ideas about how might I explain this. Yeah, so you're along the right idea. Remember what this means again. X going off to negative infinity. I can take negative 10,000, negative 100,000, negative 1 million. What is happening as I plug those numbers in, as I increase my X? So if I go from negative 1,000 to negative 1 million, what's happening overall? It's getting larger. So again, as I plug in larger negative values, 4x to the 16 is getting larger as well. In particular, larger in the positive direction. And if you wanted to, you could graph this 4x to the 16th. You would see on the left is going up. So for A, I would say that, yeah, we're going to get infinity here. Notice here that I'm not exactly saying I'm plugging in infinity because, again, infinity is not really a number. But I'm going to use that informal wording. What about for part B? The limit as x approaches positive infinity of 1 over x. Again, I want you to think, what would happen if I plugged in 10,000, then 100,000, and then 1 million? What's happening to this expression? It's getting smaller. Because imagine, if I had 1 over 100, that's a small number. If I did 1 over 1,000, that's even smaller. If I did 1 over 10 billion, that would give you 0.000001 after a while. So my question here will be, what number am I approaching in particular? So if I plug in 10, for example, I would get 0.1. If I plug in 100, I get 0.01. 1,000, 0.001. What's happening as I increase my plug-in? What number am I getting closer to? 0. So I'm going to claim this one is going to be 0. So one of these, they gave me infinity. The other one, it gave me 0. What was the big difference between these two functions I was looking at, between A and B? So in particular, the thing I'm noticing, just as an initial thought, is that one had an X on the bottom, and the other one was just a plain X, essentially. Okay, so that might be a good starting spot. What if I had something like this, though? Let's be even broader. Part C. What if I had the limit as x goes to negative infinity of, let's do x plus 1 over x squared plus 3. This one's definitely not as clear, per se. I'm definitely dividing by some x's. But I want you to think about long-term behavior. On the top, if I just focus on x plus 1, and I plug in very large negative values, x plus 1, that's still going to be a really big negative number, right? So on the top, x plus 1. If I plug in a large negative number, add 1, that's still a big negative number, right? What about on the bottom, x squared plus 3? If I plug in a large negative number, what do you think is going to happen on the bottom? It's going to be a large positive number. Which one of these two numbers in general do you think would be bigger? Would it be a larger negative number or a larger positive value? Larger positive. How did you know that? Not just the sign, but let's say in magnitude. So overall, we have a huge negative number and a huge positive number. You also tell me that the huge positive number is even larger. Like for example, if it was like negative 1,000, the positive number would be like what number is it? 10,000 squared, for example. I claim that looking at this, my denominator will have a larger value always than the top. How do I know that the bottom will always be a larger, not just in sign, but magnitude overall? Well, look at our power on the top and the bottom. What's the power on top? 1. What's the power on the bottom? Which one is generally bigger, x or x squared in most cases? X squared. So if I look at this, I'm saying the power on the bottom is larger. In other words, the power on the bottom, the denominator outpaces the top. So as I increase my x, the bottom is going to get even larger, and the gap between the numerator and the denominator is going to get larger and larger. What I'm going to claim is that this is going to be 0. And we can test this if we want to. I want you to plug in negative 10,000, negative 1 million, negative 10 billion. And you're going to see that slowly we're going to get closer and closer to 0. We can even do that with small numbers. Let's say if I plug in, let's do negative 1, for example. What happens if I plug in negative 1? Someone do that for me. And someone do negative 10, and someone do negative 100. Or I can do this very quickly as well. We'll get, just to prove a point, if I plug in negative 1, I'll get 0 over 4, which is 0. If I plug in negative 10, I'll get negative 9 over, 97? 103, right? Negative 10 squared, we get 100 plus 3. Down here on the bottom, we get negative 99. What's negative 100 squared? Plus 3, we get 1, 2, 3, 10,003. So if I compare this, how fast is the top growing? It's growing pretty slow, right? 0, negative 9, negative 99. You can imagine the next one will be negative 999. But what about the bottom? The bottom is growing much faster between these two. The bottom's going 4, 103, 10,000, 10,003. Next one's probably 100,003 or something like that. In other words, I'm doing this to show that the bottom is going to outpace the top portion. That's a good question. So that would mean the top outpaces the bottom. That will actually, we'll see, turns out that we go off to either infinity or negative infinity, depending on the sign. We actually saw that up here, because can't I just write this? The top is definitely outpacing a plane 1. So even though I didn't write it here, that principle still applies. And if you look at this, we're going to see that we're going to get closer and closer to our values. So what I'm going to do is I'm going to give you all a theorem that's going to give us a quick way to evaluate all these without actually having to be like, what happens if I plug stuff in? So, theorem. Let's see if I want to plug this in. So, it's going to have 4 parts. The limit as x approaches plus or minus infinity of x to the n power is infinity if n is even. So if I have x to an even power, I don't care if it's x going off to negative infinity or positive infinity, my answer is going to be a plane infinity. Why does it not matter if I'm saying x going off to positive or negative infinity? Why does that not matter? Yeah, what happens whenever I take any number to an even power? Is it going to be positive or negative? Positive. So like, for example, a negative number squared, that's positive. And clearly if I put it in a positive number and take it to a power, that's still positive. Next is the limit as x goes to infinity of x to the n is infinity. And the limit as x approaches negative infinity is negative infinity if n is odd. So if I have an odd power, then we're pretty much following through with the same sign. For the same reason, if I take a negative number to the odd power, it's still negative. If I take a positive number to an odd power, that's also positive. Shrink this a little bit, move this up. C. Well, if I take the limit as I go to this one, it doesn't matter, x to a negative power. Does anyone remember what does a negative power mean? Yeah, 1 over x to whatever power. So like x to the negative second power, that's 1 over x squared. So if you want, just for your notes, you could write this just to remind yourself. 1 over x to the n. What do y'all think this limit is going to be, regardless on if it's positive or negative infinity? 0. Again, I can imagine 1 divided by a huge number, you're going to get 0.00000001. And the last one, probably the one that I want to talk about in particular, part D, is if I take the limit as x approaches plus or minus infinity of a polynomial. Let me write it like this. an x to n plus an minus 1 x to n minus 1 plus dot 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 a0. So a polynomial like x cubed plus x squared, something like that. Actually, it will turn out that we only care about the limit of the largest power. So for example, if you had this long polynomial and it started off with like x to the 45th power, you only care about that first portion. I don't care what's happening afterwards. So this is something that you don't have to write, but just to talk about part D, again, if I had the limit as x approached infinity 3x to the 45th power plus x squared. What this part D is saying is I only care about the first portion. I would only care about, again, the limit of 3x to the 45th power. But why is that the case? Why would I only care about the largest power in a polynomial and its coefficient, technically? First off, it's the largest x part. Which one of these is going to dominate the behavior more in the long run? 3x to the 45th power or an x squared? The 45th power. That's really going to determine what's going on in the long run. Even though in the beginning x squared may have a big effect, but as I increase my x values, that x squared is not going to mean much in the long run. The 45th power is really what's going to do all of my work. So we're going to apply these four parts of my theorem. And I'm going to claim that we're going to solve all of these limits, each one within less than 10 seconds each, using some very quick rules. So right now it looks like I'm just drawing a bunch of theorems up, but you'll have to trust me for just 20 minutes, give or take, for us to get through this quickly. We just have to get through the theory part. You'll see that actually is not too bad once we get through it. All right, so on paper, let's do this example. Example 3, evaluate as per usual. Let's do the limit as x approaches negative infinity of 6x to the 11th power minus x plus 3. Question is, how can I evaluate this? What rules? Obviously, for our first time, we'll talk it out. What's the first rule that I can probably apply from those list of A, B, C, D? Yeah, so there's a couple things depending on how I look at it. The first one that stands out to me, again, just for the sake of notes, I only care about the highest power and its coefficient. So if I wanted to, I could write this. 6x to the 11th power. Again, I don't care about the lower power terms. I only care about the highest power and its coefficient. Emphasis on and the coefficient. Walking you through this one, I can take out a 6 if I wanted to and get the limit of x to the 11th power. Remember, from our very first couple of lectures, we can always take out a factor, like a constant multiple law. What's the limit of x to the 11th power as x approaches negative infinity? 6 times. So, from my rules, I know that this has to be positive or negative infinity. Is it positive or negative? So the power is odd. What happens whenever I take a negative number to plug in and take it to an odd power? It's going to end up being negative, right? Negative number to an odd power. So like negative cubed, that's still negative. Broadly speaking, what's 6 times negative infinity? Negative infinity, an even larger negative number. So my question here, our answer is negative infinity, but did I really have to write out every single step there? No, if I really wanted to, the quick way that we're going to start doing this is polynomial. I only care about the highest power. I don't care about this. X to the 11th power. If I take a negative take it to the 11th power, that's negative. What's a negative number times a positive 6? Well, negative infinity times a positive 6, negative infinity. This is how I mean we're going to go through these really quick. We only care about the highest power and the coefficient. Why do I need to care about the coefficient, by the way? So in particular, why do we need to care about that 6? Because here it didn't really do anything. Yeah, if this was a negative 6 in front, it would change it from negative infinity to positive infinity. So the 6 itself doesn't matter, but I care that it was a positive 6 is the big deal. All right. How about this one then? Part B. Let's take the limit as x approaches infinity. Let's try 11 plus 5x cubed. Be a little bit careful with this one. What's the limit of a sum? We know that we can do the limit of each one individually, right? This is where I have to be a little bit careful. Again, we don't always have to write this, but just for notes, I can split this into two parts. What's the limit of 11? Cool, 11. What's the limit of this one on the right? 0. Why? It's a negative power. We said if we take the limit of a negative power, then it's 0. What's 11 plus 0? 11. I do want to take a pause here to talk about something. Why is it in the previous one I was allowed to ignore the rest, but this one I had to do some splitting? This one was not a polynomial. I was only allowed to do that thing where I ignored the rest whenever I just had something like a set of positive powers, like x cubed plus some other stuff. This one had a negative power, so I just had to be a little bit more careful with my work. Let's do one more for this example. Part C, let's do the limit as x goes to negative infinity, negative 3x to the 102nd power plus 4x to the 100th minus 8. Someone give me what will be our final solution here. What was that? Negative infinity. Let's see why. Is this a polynomial? Does it look like just like a number, x to a positive power, all the way down? Yeah, I don't have any negative powers, so I'm not worried about splitting. Therefore, I'm just ignoring the lower ordered terms. What's my power? Is it even or odd? Even. What happens whenever I take a negative number to an even power? Yeah, it becomes positive. What's a positive infinity times negative 3? Negative infinity. This is how we're getting negative infinity. So for right now, we're pretty much only talking about two cases where I get 0, maybe plus or minus something, or I get plus or minus infinity. We're not going to have enough time today, but we're going to talk about what if I have a rational function, like x is on the top and x is on the bottom. Again, we're going to define some rules for that. Probably not today because we're running low on time, but we're going to see that the end goal is we're going to look at a problem and we're going to say the answer instantly. just based on the power on the top or on the bottom, and or the bottom. So any questions so far on this topic? Again, this one's a little bit different because we're trying to analyze our end behavior. What happens if I keep on growing large in a positive or negative direction? I'm going to do one more note about this. What I'm going to say is going to be considered very informal language, but it might help with following what we've been doing. I want you to imagine that we can plug in positive or negative infinity, for example. Again, big air quotes where I'm plugging in infinity. First off, for this, do y'all agree that we don't have to worry about these lower order terms? We don't have to worry about these because I only care about the largest power. Well, if I take this and I want to use this rule of, let's say I plug in negative infinity, just for concept wise, negative infinity to an even power, it's going to become positive infinity. Huge number, huge negative number, even power, it's a huge positive number. A negative number times positive infinity, we get negative infinity. So even though I am breaking some rules talking about infinity is not really a number, it can help us a little bit concept-wise. Whenever we get to those about rational functions, just as a preview for next time, you don't have to write this because we'll cover it next time. You're going to see something like this. I'm going to give you something like, I'm going to claim that once we're done with that class on Wednesday, you should be able to look at this and give the answer immediately. Does anyone have a general guess about what might happen here? 0. Why? The power on the bottom is larger, then it's going to become 0 because you have a huge number on top, but an even huger number on the bottom. What if I had something like this? Let me change this to 213 on the top. Which one has the higher power, the top or the bottom? The top for sure. If I were to look at this, then we're going to find out that this answer is going to be positive or negative infinity. We'd have to do a little bit more work. In this case, it's going to be, this one's going to be positive infinity in particular. And then the last scenario we're going to talk about, let me add a number here. It is going to be 1/3. Does anyone have any insight about where these rules might be coming from? So let's talk about this. Would y'all agree the top is a polynomial, the bottom is a polynomial? What did I say about polynomials? We can ignore the lower order terms, right? In a sense, I can ignore this. Can I simplify what's left over? 45 over 45, what am I left with? Even before, whenever this was like this simplified into 1 over 3x to the 44. What was our rule for that? It goes to 0. So this is going to be combining those rules that we did today and the ones we've done way back in the beginning. I didn't show the examples, but remember we can split it from the limit on the top, limit on the bottom, stuff like that. So this is why I mean that we're going to be able to look at these limits and then answer it very quickly based on simply the power on the top and the largest power on the top and the largest power on the bottom. Because we're going to be able to ignore those lower order terms. Just like right here, I can ignore the rest. Well, this one's supposed to be squared. That's my bad. Because that's a higher power. But that's what we're going to be doing on Tuesday. And just as a last reminder, are we coming to class on Monday? No. Why? It's Labor Day. Do we have a homework assignment due? No. Enjoy your Labor Day away from calculus. I'll see y'all on Tuesday. Yes. Let me zoom out here. Yes. Um, Send me an email and then I'll give you like a 1 week extension. Well, technically 2 weeks because it's a weekend. So just send me an email so that I can open it. Enjoy whatever y'all have planned. Yes. If all of them were negative, so it's a little bit more weird, but let's say somehow x approach infinity. So are you talking about where we had x on the top and the bottom? Okay, yeah. So let's just say I have this one somehow plus some other junk, x to the negative 15th power. Let me erase this while I'm at it. Plus, I don't know, x to negative 11 power, something like that. So again, we're going to be a little bit vague here. Which one of these is more or less, how do I want to word this? If I want to be technical, can't I write this as the limit as x goes off to infinity? This one's 1 over x to 13 plus 1 over x to 12. Because that's just a negative power, right? Same thing here. Oops, not negative 15. 1, 15 plus 1 over x to the 13. Oh, 11. Oh, I wrote 13. All right, and then we can do the limit of the top. What's the limit of this part right here? 0. What's the limit of this? And then I made a mistake here because the bottom's going to be 0 too. But in other words, you just do it separately. But the good news is, for the most part, we're dealing with only positive powers, almost always.
So in this case, we can't take the bigger power on the negative side?
And it's because we technically yes, but I'm going to say technically because this is technically not a polynomial. A polynomial only has positive powers. It doesn't have negative powers. So that's why I'm saying yes, but not for the same reason. Mm-hmm.
Sorry I was super late. Then I didn't see last night. But did we just go over like more
Here we just talked about a limit at infinity. What happens whenever this instead of a number, it's infinity. Yeah, so it's mainly that type of stuff. Um, we're going to talk about like and what a horizontal asymptote is for the most part. So I will be posting the notes probably sometime tomorrow or Saturday, so that you can review it. But what was that?
So we'll be posted to shop tonight.
Yeah, just not tonight because I still have to type them up because usually all the notes I do everything from memory. Yeah. So yeah, you can expect that either tomorrow, if not tomorrow, Saturday. Mm-hmm. Yeah. If we were talking about this broadly, it really boils down to growth behavior in the long run.
Yeah, we like when I took it in like high school, we just learned Betsy, Botu, and Bobo. That's pretty much the cheat code.
Yeah.
Like the bottom coefficient. I literally, all right, okay, all right.
No, because I just be, I be sitting there like, what is that?
Going.
And I be trying to pay attention and look, because I record each lecture on my phone to go back and listen to them. And I still be like, I don't know.
Also, you don't need to record because they're already recorded.
I know. Like, I started recording on like the first class. Like, that was before you had even started recording. So I was just sitting there like, if I get this on the test, I'm screwed. That's what
So some possible consolation is that after this chapter, it's almost like we're going to abandon all this. And then we're going to move into a completely, it is related theoretically, but in terms of how you approach the problem, it's going to be a lot different. Because in the future, it's going to be something like this. And then it'll be like, find the derivative. And then this one's like a one-step problem. But we just have to get through this limit chapter because everything we do in chapter 2, the theory comes from the limits. Usually, I say that for a lot of students, the first one, usually honestly, the first one ends up being people's worst because it's a new semester and it's limits. Yeah, this is going to be 12x cubed. And we're going to learn how we get that pretty much instantly. And then later, depending, we might do some stuff like this that's a little bit more complicated. Like that, how do you get the derivative of all this stuff? Yes. Low.
Once I get past this first one, I'm pretty self-restricted. It always take me, my first semester